Hello there, and welcome to the Black Hole Files. I'm so glad you've joined me tonight. Whether you're winding down from a long day or simply looking to float gently into sleep, you've found the right corner of the cosmos. Tonight, we're gazing up and out into the galaxy we call home. That soft, shimmering ribbon of stars stretching across the night sky. Some call it the Silver River, others the backbone of night. To us, it's the Milky Way. But what is the Milky Way, really? Where are we within it? And how does it quietly carry us on a journey that spans hundreds of millions of years? In this bedtime voyage, we'll drift through the spiral arms, explore stellar neighborhoods, meet ancient globular clusters, and even tiptoe near the mysterious black hole at our galaxy's heart. We'll learn how stars live and die, how dust hides entire realms from view, and how, despite the grand cosmic expansion, our Milky Way sails gracefully through space, like a glowing lantern in the dark. So settle in, take a deep breath, and if you'd like, let me know in the comments. Where in the world are you listening from tonight? Let's begin our quiet journey through the galaxy, and let the stars guide us gently to sleep. Under a clear, dark sky, the Milky Way appears as a misty river of stars arching overhead. In this serene band of light, our galactic home seen from within, countless stars weave a tapestry across the night. On a still, starry night, we gaze up and see a pale, milky band stretching across the sky. This soft glow is our Milky Way galaxy, the great island of stars we call home. We live deep inside this galaxy on a planet orbiting a rather ordinary star, the Sun. To imagine our place, picture the galaxy as a vast, shining city of stars. If the galactic center were a busy downtown, our solar system would lie out in the quiet suburbs about 25,000 to 30,000 light years from the center. Here on these outskirts, we reside in a smaller neighborhood known as the Orion Spur, or Orion Arm. A local spiral arm segment nestled between two larger spiral arms named Sagittarius and Perseus. In this comfortable locale far from the crowded center, the night sky is peaceful and the stellar traffic is sparse. From our vantage point inside the galactic disk, we see the Milky Way as a luminous band. It gets its name from its milky white appearance, as if someone spilled a faint trail of milk among the stars. Cultures around the world have given it poetic names. The Chinese know it as the Silver River, and the Kalahari Bushmen call it the backbone of night. Lying in this galactic plain, we peer through dense swirls of stars and interstellar clouds. The light of millions of distant stars blurs into a cloudy glow. Some dark patches mar the glowing band. These are vast clouds of interstellar dust blocking the starlight. On the clearest nights, far from city lights, this shimmering band of the Milky Way becomes visible to the naked eye, reminding us that we are inside a flattened disk of stars, gazing toward our galaxy's central regions. Though it feels like Earth is stationary beneath our feet, our planet and entire solar system are in motion around the galaxy's center. The Sun carries us in a grand orbit drawn by the Milky Way's gravity. How long does this cosmic journey take? About 230 to 250 million years for one orbit. Astronomers often call this span of time a galactic year. In other words, the last time our solar system was at this exact spot in the galaxy, dinosaurs were just emerging on Earth, and mammals had yet to evolve. It has taken all of human existence, and much more, for us to move only a tiny arc along this enormous orbit. In the roughly 4.5 billion years since the Sun and planet formed, we've completed around 20 orbits of the Milky Way. A galactic year is such a vast span that it's almost beyond comprehension. A slow, stately circuit around the galactic center, during which continents drift and species come and go. Our solar system's orbit is not a perfect circle, and it doesn't stay perfectly flat either. We follow a gently undulating path, sometimes bobbing a little above or below the galactic plane as we go. This means that every 30 million years or so, we drift through the central plane of the galaxy's disk and then back out, in a subtle up and down motion. Some scientists have wondered if these passages through the crowded mid-plane might disturb comets or trigger extinctions on Earth, but evidence for any regular cycle of extinctions is inconclusive. Still, it's fascinating to imagine that as we orbit, the environment of space around us slowly changes. Sometimes the sun is slightly above most other stars, sometimes below, like a ship on a gentle cosmic sea. Even the speed of our journey is mind-boggling. We are moving at roughly 828,000 kilometers per hour around the galaxy's center. That's about 230 kilometers every second, or nearly 515,000 miles per hour. At this tremendous speed, we could circle the Earth's equator in just a few minutes. Yet space is so vast that even at this rate, it takes hundreds of millions of years to complete one lap around the Milky Way. From our perspective on Earth, we don't feel this motion at all. The stars are so distant that their patterns change only slowly over tens of thousands of years. But make no mistake, we are hurtling through the galaxy on a majestic voyage carried by the sun's own orbit around the galactic heart. Yet let's step back in our imagination and picture the Milky Way from afar. Our galaxy would appear as a magnificent spiral, like a giant pinwheel made of stars. It is a spiral galaxy with curving arms that wrap around a bright central hub. In fact, astronomers classify it as a barred spiral galaxy, meaning it has a bar-shaped concentration of stars at its center from which the spiral arms unfurl. The Milky Way is immense, about 100,000 light-years across from edge to edge. A light-year is the distance light travels in 1 year, nearly 10 trillion kilometers, so 100,000 light-years is almost unimaginably large. Our galaxy's disk, where most of the stars lie, is thin relative to its width, roughly 1,000 light-years thick in the main stellar disk. If the Milky Way were scaled down so that it was as wide as North America, the disk's thickness might be just a couple of kilometers, a very flat shape overall. The Milky Way's spiral arms are the most striking features of its structure. These arms are like huge stellar highways curving out from the center, filled with stars, gas, and dust. There are two major spiral arms that researchers generally agree on, named Perseus and Scutum Centaurus, which are prominent and long. In addition, our galaxy has smaller arm segments or spurs. One of these is the Orion arm, also called the Orion spur or local arm, which is the little region our sun calls home. Our Orion arm is sandwiched between the Perseus arm, outside of us, and the Carina Sagittarius arm, inside toward the center. The Orion arm is modest, a less flashy spur compared to the major arms. Think of it as a side road off a big highway. It spans a few thousand light-years across, winding between the giant arms on either side. Astronomers initially thought the Orion arm was short, about 10,000 light-years long, but newer studies suggest it extends more than 20,000 light-years, making it more significant than once believed. Crucially for us, the Orion arm provides a relatively calm neighborhood in which the sun orbits, possibly sheltering us from some of the more violent cosmic events that occur in denser regions of the galaxy. Illustration. A face-on view of the Milky Way reveals its spiral design. The galactic disk contains long, curving arms, two prominent ones named Perseus and Scutum Centaurus, and smaller ones like Sagittarius and Orion. Our sun's location is marked on the Orion arm, a minor spur between major arms. Within the spiral arms, stars are born in great numbers. These arms are not static like solid arms of a pinwheel. They are more like traffic jams of stars and gas that move around. Gas and dust clouds orbit the galaxy and can get squeezed as they enter an arm region, triggering the collapse of clouds and the birth of new stars. That's why many of the bright, young stars, often blue in color, are found in the spiral arms, along with glowing clouds of gas from which they formed. The arms tend to shine brightly because of these hot young stars and star clusters, whereas the spaces between arms have somewhat fewer stars, mostly older ones that drifted out. In a way, spiral arms are like stellar nurseries and traffic jams combined. Material slows down and bunches up, and stars ignite, then move on, and the pattern of the arm itself also winds around over time. Interestingly, studies suggest that spiral arms are not permanent. They can form and disperse over hundreds of millions of years, but the Milky Way currently has this graceful spiral structure that has likely persisted for a long time. Our galaxy's overall type of barred spiral is quite common in the universe. In fact, 2/3 of spiral galaxies have a central bar structure. The Milky Way's bar is relatively small compared to those of other galaxies of similar size, but it still plays an important role by channeling gas toward the center and possibly helping to maintain the spiral arms. When we compare the Milky Way to other galaxies, we find it is large and massive, but not the largest type. There are giant elliptical galaxies far bigger, with trillions of stars, often found in the cores of galaxy clusters. By contrast, the Milky Way has on the order of a few 100 billion stars, an impressive number, but Andromeda, our sister galaxy, may have close to 1 trillion, and some galaxies are even larger. Many galaxies are much smaller than the Milky Way. Dwarf galaxies with only millions or billions of stars are common. So our Milky Way is something of a mid-sized to large spiral, bigger than most galaxies, but overshadowed by the truly giant ones. It's also broadly similar to Andromeda, which is another large barred spiral. Both have disks and arms, older central bulges, and massive halos of stars and dark matter. One fun fact is that the most common stars in the Milky Way are not the bright ones we see with the naked eye, but rather tiny red dwarf stars that are so dim you need a telescope to notice them. Red dwarfs, classified as type M stars, make up an estimated 60 to 70% of all stars in our galaxy earthsky.org. These stars are cool, faint, and long-lived. Many will outlive larger stars by trillions of years. Our Sun, by comparison, is a fairly average star, larger and brighter than a red dwarf, but much smaller than the big blue-white stars that shine prominently in the spiral arms. The Milky Way contains the whole menagerie of stellar types: hot blue giants, yellow suns, orange dwarfs, red dwarfs, as well as the remnants of stars' lives, which we will soon explore. All these stars, in their multitude, orbit within the structure of the galaxy, each following its own path, yet together creating the grand swirl we recognize as the Milky Way. At the very heart of the Milky Way lies a mystery veiled in darkness, a supermassive black hole named Sagittarius star, pronounced Sagittarius A star. This central black hole, with a mass of about 4 million suns packed into a tiny region, is the mighty yet invisible engine of our galaxy's core. It's fascinating to think that at the center of all the stars we see, there is something we cannot see directly. A true gravity well so deep that not even light can escape it. For a long time, Sagittarius star was inferred from the motions of stars. We observed stars whipping around an unseen object, moving astonishingly fast, which indicated a huge mass in a small space. Everything in the galaxy orbits the center, and Sagittarius A star sits there like a silent anchor. However, it's important to note that most of the Milky Way's mass is not in the black hole. The black hole is massive, but the combined mass of the galaxy's stars, gas, and dark matter is far greater. Still, Sagittarius A star provides a deep gravitational point that strongly influences the orbits of stars in the inner core region. For many years, Sagittarius A Novae was an unseen giant, but in 2022, astronomers achieved a groundbreaking feat. Using the global network of telescopes called the Event Horizon Telescope, they captured the first ever image of the faint shadow of this black hole. The image showed a fuzzy ring of light and glowing gas orbiting near light speed, surrounding a dark center where the black hole resides. This was an extraordinary confirmation that this gentle giant truly is a black hole. A historic first glimpse of Sagittarius A, the Milky Way's supermassive black hole captured by the Event Horizon Telescope. The image, revealed in May of 2022, shows a glowing ring of hot gas surrounding a dark shadow. This provides direct evidence of the gentle giant lurking at our galaxy's center. Despite its fearsome reputation, Sagittarius A star is relatively quiet as far as black holes go. It's not currently gulping large amounts of material, so it doesn't emit powerful jets or radiation that we can easily detect in visible light. In fact, astronomers sometimes dub it a gentle or dormant giant, because it's only feebly feeding on bits of gas. But it wasn't always so quiet. Evidence suggests that in the past, Sagittarius A star had periods of activity. For instance, enormous bubbles of high-energy particles, observed in gamma rays and X-rays, billow above and below the galactic plane. These Fermi bubbles are thought to be leftovers from an ancient outburst by our central black hole a few million years ago. Even a sleeping dragon can stir occasionally. Sagittarius. A star, though, likely gave off a blaze of energy in the past that carved those giant bubbles, though now it slumbers with just occasional flickers of X-ray flares. The significance of Sagittarius as star to us is profound in multiple ways. It anchors the inner galaxy structure, the orbits of stars in the inner bulge, and around the center are determined by its gravity, along with the mass of millions of other stars there. We have observed entire stars, such as a famous star called S2, racing around Sagittarius A star in highly elliptical orbits, coming as close as just a dozen billion kilometers, which is very close astronomically, and then swinging far out again. These stars move at breakneck speeds, several thousand kilometers per second, near the black hole, allowing astronomers to test Einstein's general relativity in this extreme environment. Indeed, watching these stars over decades provided the proof that Sagittarius A is a supermassive black hole, as only something so massive and compact could make stars orbit so rapidly. Sagittarius. A star also represents a window into understanding black holes in general. It is the closest supermassive black hole to Earth. Still 26,000 light-years away, so no danger to us. And thus the easiest one to study in detail. The successful imaging of its shadow in radio waves was a milestone that deepened our collective understanding of how black holes accrete material and affect their surroundings. It's like having a relatively tame tiger in our cosmic backyard that we can observe to learn about all tigers. While Sagittarius A null itself doesn't hugely affect our everyday life out here in the spiral arm, its influence is mostly local to the galactic center. It is intrinsically part of what makes the Milky Way what it is. It likely formed very early in the galaxy's history and might have grown by merging with other black holes or swallowing gas as the Milky Way evolved. Some theories even suggest feedback from active bursts of Sagittarius A star could heat and push gas around in the bulge, potentially influencing star formation rates there. In essence, this black hole is a key chapter in the story of our galaxy's life. It sits in peaceful darkness now, a massive guardian of the central stars, while the whole galaxy quietly revolves around the gateway to nothingness at the core. Knowing it's there, and finally seeing evidence of it, gives the Milky Way a sense of depth and wonder, as if our galactic home is a hidden heart of gravity that we are only beginning to understand. Surrounding the galactic center and the black hole is a dense central concentration of stars known as the galactic bulge. If the spiral arms are their galactic suburbs, the bulge is the downtown core of the stellar city. It appears as a rounded, bulging swarm of stars in the middle of the galaxy, sticking out above and below the flat disk. In the Milky Way, this bulge is not perfectly spherical. It's somewhat elongated or peanut-shaped in profile. It spans about 10,000 light-years across, which is about 1/10 the diameter of the entire galaxy. Packed into this relatively small volume are perhaps 10 billion stars, primarily old, reddish stars that formed in the galaxy's early epochs. The bulge shines with a warm, steady glow of these old stars, many of them red giants. If we were located near the center, the night sky would be ablaze with starlight. In fact, if our sun were deep in the bulge, the density of nearby stars would make the sky hundreds of times brighter than what we see from Earth, likely washing out the darkness of night entirely. The role of the galactic bulge is akin to the hub of a wheel. It's a central mass concentration that the rest of the galaxy's disk rotates around. The bulge's gravity, together with the black hole and the inner dark matter, provides a strong pull that helps keep stars in the inner galaxy moving in their paths. The spiral arms often spring from the ends of the central bar bulge structure, so in a barred spiral like ours, the bulge and bar essentially launch the arms outward. In the Milky Way, the bar extends across the central bulge, and its rotating presence may funnel gas inward, and influence star formation in the core. The bulge itself, however, has very little free gas or dust. It's mostly a repository of older stars, meaning that new star formation is minimal inside the bulge. Most of its stars formed billions of years ago when the galaxy was young, and since then, not much cool gas remained there to form new stars, aside from some near the very center. The lack of young blue stars is why the bulge looks yellow-red. It's dominated by aged stars like red giants and red clump stars. The stars in the bulge move differently from those in the disk. In the disk, stars, including the Sun, mostly follow orderly circular orbits, all going in the same direction around the center. In the bulge, however, stars swarm in more random, elliptical orbits oriented at many angles. It's somewhat like a beehive of stars buzzing around the center in all directions. This random motion is why the bulge is spheroidal in shape. The stars don't align into a flat disk, but instead form a ball, or peanut-shaped ball in our case, due to their varied orbital tilts. These orbits can be elongated, and bulge stars often plunge toward the center and then back out, much like comets do in the solar system, but on a galactic scale. The bulge's dynamics, the mix of random orbits, are reminiscent of elliptical galaxies, which likely reflects how the bulge formed, possibly through early mergers or rapid collapse of the protogalactic cloud. Interestingly, our Milky Way's bulge might not be purely a classical bulge. Some evidence suggests it has characteristics of a disk-eye bulge, or pseudo-bulge, meaning that the central bar and inner disk dynamics have shaped it into a different structure over time. In a pseudo-bulge, stars still have more ordered orbits aligned with the disk, compared to a chaotic classical bulge. The Milky Way's bulge likely has a bit of both behaviors, and some stars in randomized orbits and some following the bar's orientation. This is an area of active research. From a storytelling perspective, the galactic bulge is like the ancient crowded core of our galaxy, a place filled with elderly stars that formed when the Milky Way was young. There are also some exotic objects in the bulge. Globular clusters often pass through or around it, and there are many variable stars, like RR Larry variables, that helped astronomers determine distances. The bulge is crucial historically. When Harlow Shapley mapped the distributions of globular clusters roughly a century ago, he noticed they centered around a point in Sagittarius. That was the Milky Way's center, deep in the bulge, far from our position. This discovery revealed that the Sun is not at the center of the galaxy, but rather offset in the disk. Thus, the bulge, teeming with globular clusters and old stars, marks the true center of the Milky Way and holds the clues to our galaxy's origins. It's a central beacon, though obscured by dust and visible light, around which the rest of the galaxy revolves. In summary, the galactic bulge plays the role of a bright and massive central hub. It houses the galaxy's oldest stellar population, and its gravity influences the inner rotation of the Milky Way. Its stars orbit in all directions, giving the bulge a spherical or bar-shaped form that stands in contrast to the flat disk. Without the bulge, and its bar, our galaxy would lack that distinctive central glow, and might not have the same spiral structure. It's a crucial piece of the Milky Way's architecture, the ancient heart of the galaxy in terms of stellar population and mass concentration. As we travel outward from the busy galactic center, we re-enter the realm of the disk and spiral arms where the Sun lives. Here in the galactic disk, and stars orbit in an orderly fashion. Almost all disk stars move in the same direction around the center and lie roughly in the same flat plane, like horses on a very large carousel. The Sun, for example, follows a gently curving path around the center along with its neighbors. These orbits are mostly circular or slightly oval, and the stars bob only a little up and down through the disk as they go. This gives the disk its thin, flat structure. Stars don't wander far from the plane, keeping the disk confined in thickness. In the disk, star orbits are nearly coplanar and aligned, which is why we see a clear band of the Milky Way. We are looking edge-on through a swarm of stars all moving in roughly the same plane. Now contrast that with the stars in the bulge and halo. In the bulge, as mentioned, stars follow randomly oriented orbits. They loop around the center at many different angles, some going north-south, some east-west, all directions, like bees around a hive. Because of this, bulge stars do not line up into a disk, but fill a ball-shaped distribution. They can get very close to the center and then travel far out of the bit, only to swing back again. Similarly, the halo. The sparse outer region of the galaxy contains old stars and globular clusters on wildly inclined and elongated orbits that bear little resemblance to the neat circles of the disk. A halo star might be plunging toward the center from far above the galaxy, cross through the disk at high speed, and exit out the other side. These stars are not confined to the plane. Their orbits form a roughly spherical pattern around the galaxy. To paint a mental image, imagine the galaxy as a spinning CD, the disk, with a fuzzy ball of stars around it, the bulge and halo. The stars on the CD, disk, move in nice circles along the disk's grooves. The stars in the fuzzy ball, bulge, halo, move every which way, some cutting across the disk, some looping high above it, then below, in no particular alignment. Disk stars tend to be younger and have orderly motion, whereas halo stars are mostly old and have disordered eccentric motion. Our Sun, being a disk star, is part of the organized rotation, which is fortunate for us. The stable environment of the disk plane likely helped life to flourish on Earth without too many wild gravitational perturbations. One consequence of these different orbital behaviors is that collisions and close passes between stars are extremely rare in the disk. Despite the huge number of stars, space is mostly empty, and similarly even rare in the halo. But the relative motions differ. In the disk, if we meet another star, it's likely going near our speed and direction, like cars on a highway. In the halo, encounters can be at much higher relative speeds and random angles, like two insects buzzing randomly and crossing paths. The Sun occasionally passes relatively near other stars, but such events are millions of years apart, and usually distant enough to have little effect. Globular clusters, the dense clusters of ancient stars that inhabit the halo, also have their own orbits around the galaxy. These orbits are typically highly elongated, eccentric, and tilted at random angles to the disk. A globular cluster might spend most of its time far outside the main galaxy, slowly arching up to a great height above the disk, then plunging through the galactic plane, moving fast to the low point, and shooting out the other side into the halo again. The Milky Way has over 150 known globular clusters, each following such a path. For example, a cluster could travel thousands of light years above the galaxy, then fall through near the center, then out to the other side, taking perhaps a few 100 million years for one circuit. These clusters' orbits show us that they are not confined by the disk. They really belong to the halo, tracing out the gravitational potential of the whole galaxy. To summarize, stars in different parts of the galaxy orbit differently. Disk stars, like the Sun, orbit in the galactic plane in the same direction, mostly circular paths. They define the thin disk structure and give the Milky Way its spiral shape. Bulge stars orbit in many directions, giving the bulge a round shape. Their paths are randomized, often plunging toward and away from the center. Halo stars and clusters also orbit on random inclined trajectories, often very elongated. They can go far above and below the disk and out to great distances, then back through. These differences reflect the history of the galaxy's formation. The disk formed from a rotating cloud, hence the coherent rotation, while the bulge and halo include older remnants of chaotic early mergers and collapses. The result is a beautiful dynamic system, a rotating disk with a buzzing halo around it, and we, riding a star in the disk, are blissfully carried along in a smooth orbit, largely unaware of the halo stars drifting by on their celestial highways above and below us. In the quiet halo of our galaxy roam some of the oldest representatives of the Milky Way, the globular clusters. These clusters are like spherical citadels of stars, each containing hundreds of thousands or even millions of very old stars packed tightly together. A globular cluster appears as a round, glittering ball, stars densely concentrated toward the center, giving it a bright core that gradually fades into to a sparse edge. The Milky Way is home to over 150 known globular clusters, and possibly more hidden by dust, and they form a nearly spherical distribution around the galaxy. In fact, one of the key observations that revealed our place in the galaxy was that globular clusters are centered on the constellation Sagittarius, meaning the clusters encircle the galactic center, not the Earth, thus indicating the true center of the Milky Way. What exactly are globular clusters? They are extremely old stellar clusters, with ages typically around 11 to 13 billion years. That means they're stars formed when the galaxy itself was in its infancy. The stars and globulars are mostly low-mass, long-lived stars like red giants, red dwarfs, and subgiants, and are notably metal-poor. In astronomy, metals means any element heavier than helium, and metal-poor indicates these stars formed before heavy elements were common, so they contain very little iron and carbon, etc. This also supports their extreme age, as they were born when the universe hadn't yet enriched the gas with many heavy elements, which are produced by generations of stars. Globular clusters orbit the Milky Way on their own paths, and these orbits tend to be very elliptical and inclined relative to the disk. A cluster might soar high above the galaxy's plane, then dive down through the disk and back out the other side. They spend most of their time in the halo's outer reaches, moving slowly at apogalacticon far out. Then they accelerate as they swing near the center. The orbits can take several 100 million years for one loop. Because they go through the crowded inner galaxy, globulars can on occasion be tugged by the gravity of the disk and other structures, but they are tightly bound groups and generally survive intact, though some may lose a few stars during close passes. To an observer within a globular cluster, the night sky would be astounding. Stars would be everywhere, much brighter and closer than we see from Earth. At the core of a dense globular like Omega Centauri and M13, there may be tens of thousands of stars in a region just a few light years across. The sky would never get truly dark because so many stars would be visible. It would be like a permanent, magnificent twilight filled with starlight. These clusters have such high stellar densities that sometimes stars can even collide or merge. In fact, there's a type of star called a blue straggler, often found in globular clusters. These stars appear unusually young and blue, and the leading theory is that they form when two older low-mass stars collide or coalesce, making a hotter, more massive star. It's a bit of renewed life in otherwise the old populations. Another interesting aspect is that globular clusters are essentially satellite inhabitants of our galaxy, and they likely formed in the early gravitational collapse of the protogalactic cloud, or even accreted from dwarf galaxies that merge with the Milky Way. Some globular clusters might have originated outside the Milky Way and were captured. For example, a few clusters have distinct chemical compositions suggesting an extragalactic origin, perhaps donated by small galaxies the Milky Way swallowed. In modern times, we see the globulars as a halo of Speakin clusters. When we plot them out, they form a spherical halo around the center, extending out perhaps 100,000 light-years or more. One cluster, Palomar 4, lies around 360,000 light-years away, far beyond the main body of the Milky Way, almost an independent little microgalaxy bound by our galaxy's gravity. How do they orbit? Much like individual halo stars, on inclined, eccentric paths that ignore the flat disk structure. We can imagine a globular cluster coming in from a high angle, getting closest to the center, perhaps a few thousand light-years away from it at pericenter, then heading back out to far reaches. During such a journey, the cluster stars all move together, swarming in orbit around the galaxy while also orbiting their common center of a mass within the cluster. The clusters are so tightly bound by their own gravity that the Milky Way's tidal forces only strip a few stars at a time. Though over billions of years, some clusters have been whittled down. Indeed, some streams of stars have been detected trailing certain globular clusters, indicating the cluster is slowly losing stars to the Milky Way's field as it orbits. In the grand story of the Milky Way, globular clusters are like ancient family elders, traveling on long pilgrimages around the galaxy. They carry the records of the early galaxy and their star's chemistry. They also provide spectacular visuals and telescopes. A concentrated ball of stars, with a shimmering, peaceful quality. For example, Omega Centauri, the largest globular cluster of the Milky Way, has several million stars, and might even be the remnant core of a dwarf galaxy that the Milky Way absorbed. It's so massive it could almost be a tiny galaxy itself. To summarize, globular clusters orbit the Milky Way, predominantly in the halo, on highly inclined and eccentric orbits. They take a few 100 million years per orbit, and can venture far above and below the galactic disk. They are relics of the galaxy's youth, orbiting steadily through the ages. When they pass through the plane or near the center, we can imagine them stirring the stellar halos slightly, like a school of fish briefly gliding through a vast ocean of stars, then heading back out into the deep galactic halo. They add to the gentle ancient character of the halo, and their presence and motions help astronomers map out the gravitational potential and mass distribution of the Milky Way, since they respond to the total gravity, including dark matter. In short, globular clusters are steadfast companions of our galaxy on its cosmic journey, moving in stately orbits that have endured for eons. Enveloping the Milky Way like an ethereal cocoon is the galactic halo, a vast, faintly populated spherical region that extends well beyond the visible spiral of the galaxy. If you could see the Milky Way from outside, you'd notice not only the bright disk and central bulge, but also a huge dim halo of star clusters and scattered stars all around it. This galactic halo is essentially an enormous sphere, or roughly spherical volume, of old stars, globular clusters, and tenuous gas surrounding the Milky Way. It reaches out to perhaps 50,000 light-years or more from the center. Some definitions say much farther if you include the extended dark matter halo. Within this halo, the density of stars is extremely low, far lower than in the disk, which is why we don't see it visibly in the sky, except via the globular clusters, or the occasional stray star. The halo can be thought of as the galaxy's attic or memory box. It contains very old stars and remnants of the early galaxy, as well as stars from smaller galaxies that the Milky Way consumed. The halo's stellar population is typically comprised of ancient metal-poor stars, population 2, which means they formed early in cosmic history and have low abundances of heavy elements. Many halo stars reside in the globular clusters we discussed, but there are also individual halo stars, some passing through the solar neighborhood at high speeds on eccentric trajectories, just visiting from the halo. These halo stars often have orbits that are not aligned with the disk, and some even orbit opposite to the disk rotation, or at right angles. It's a very stirred-up population, indicative of the Milky Way's tumultuous youth and mergers. One of the most important components of the halo is something we cannot see with our eyes or even normal telescopes: dark matter. Astronomers have deduced that the Milky Way is embedded in a huge halo of dark matter that extends far beyond the visible halo of stars. This dark matter halo contains most of the galaxy's mass, perhaps 85% or more of it, and its gravity affects everything from the rotation of the galaxy to the motions of satellite galaxies. While dark matter emits no light, we feel its presence through its gravitational pull. For example, we find that the outer parts of the Milky Way, like the Sun's orbit and beyond, rotate faster than they would if only visible matter existed, implying an unseen mass is providing extra gravity. This is a classic sign of a massive dark halo. So when we speak of the galactic halo, we often mean both the visible halo of old stars and clusters, and the invisible halo of dark matter that far outweighs them. What mysteries does the halo contain? Several, and they are intriguing. The nature of dark matter. The halo's dark matter is one of the biggest mysteries in astrophysics. We know it's there due to gravitational effects, but we don't know what it's made of. Perhaps exotic subatomic particles. It does not interact with light, making it essentially invisible. The Milky Way's dark halo extends maybe out to 200,000 light-years or more, and forms the scaffolding that holds the galaxy together. Understanding this dark component is key to understanding the galaxy's overall mass and evolution. The missing baryon problem. For a long time, astronomers had a missing matter issue. When they calculated the expected amount of normal matter, baryons, protons, neutrons, etc. In a galaxy like the Milky Way, based on cosmic proportions, about half of it seemed unaccounted for by stars and known gas. A clue to this mystery came from observing the halo in X-rays. The Milky Way is surrounded by a halo of very hot gas, millions of degrees, extending hundreds of thousands of light years. Using NASA's Chandra X-ray Observatory, scientists found evidence of this large, tenuous halo of hot plasma, with a mass possibly comparable to all the stars in the galaxy. If confirmed, this could solve the missing baryon problem by showing that a lot of the Milky Way's ordinary matter is not in stars at all, but in this extremely diffuse halo gas. This halo gas is so thin we don't notice it directly, but it can absorb and emit X-rays. It's a bit like an enormous sparse atmosphere for the galaxy. Such a discovery tells us that galactic halos are not empty, but contain significant amounts of matter in forms that are hard to see at optical wavelengths, satellite galaxies and streams. The halo is also the stage where the Milky Way interacts with its small satellite galaxies. We have neighbors like the Magellanic Clouds, two dwarf galaxies, and others like the Sagittarius dwarf spheroidal galaxy. As these satellites orbit and collide with the Milky Way, they can be torn apart, leaving behind streams of stars in the halo. Indeed, we observed long stellar streams arc across the sky. These are remnants of dwarf galaxies or globular clusters being assimilated. One famous example is the Sagittarius stream, a river of stars snaking through the halo, debris from the Sagittarius dwarf galaxy that is in the process of being cannibalized by the Milky Way. These streams are like ghostly footprints in the halo, clues to past mergers. Mapping them is a bit like archaeology, helping us reconstruct how the Milky Way grew by devouring smaller systems. The halo is full of these tidal tails, many and only recently detected with sensitive surveys. They are mysterious in that we often have to trace them and figure out which object they came from, like unraveling an old crime scene. Hypervelocity stars. Occasionally we find a star moving so fast that it is escaping the galaxy. Some of these hypervelocity stars likely come from interactions with the central black hole, flinging a star out at great speed, or from an incoming galaxy. These travelers end up in the halo, racing outward. They are rare, but they remind us that the halo can host some fascinating individual stories. A star that might have once been in the disk or center, now doomed to drift alone at intergalactic space. Magnetic fields and cosmic rays. The galactic halo also contains magnetic fields and cosmic ray particles that diffuse out of the disk. We detect radio halos around galaxies indicating relativistic electrons spiraling along magnetic field lines that extend into the halo. The Milky Way has a magnetic field that, while weak, permeates even the halo. How these fields are generated and maintained is an ongoing area of study. Additionally, the Fermi bubbles I mentioned earlier, two lobes of high-energy gamma-ray emission towering approximately 25,000 light-years above and below the center, are technically part of the halo environment. They are a mystery related to an energetic event, likely the black hole's past activity or burst of star formation, that blew hot gas out of the disk into the halo. In essence, the halo is a repository of our galaxy's secrets: dark matter, hidden hot gas, stellar remains of eaten galaxies, ancient clusters, and the limits of our galaxy's reach. It's mostly invisible and untouchable to our usual stargazing, but it dominates the galaxy in mass and size. If the Milky Way is like a glowing lantern, the halo is the nearest invisible globe around it that shapes the lantern's glow. We mostly see the bright light of the lantern's interior, the disk and bulge, but it's the halo that provides the structure in which the lantern sits. As we continue to study the halo with sensitive instruments like X-ray observatories for hot gas or gravitational measurements for dark matter, we slowly illuminate these mysteries. One poetic thought: as the Milky Way moves through the cosmos, our galaxy's halo might brush against the halos of other galaxies during close passes or future collisions, like with Andromeda. Halos could merge or spark new phenomena in such encounters. In the meantime, our Milky Way drifts with an enormous, unseen halo around it, like a subtle aura. Within that aura float the oldest stars and clusters, and an abundance of dark mass. a reminder that even in the quiet darkness far from the galaxy's bright center, there is substance and story, quietly influencing the fate of our galactic home. Our Milky Way is not an island unto itself. It lives in a neighborhood of galaxies bound together by gravity. The most prominent of these neighbors is the Andromeda galaxy, Messier 31, a majestic spiral slightly larger than the Milky Way and about 2.5 million light-years away. Together with a collection of smaller galaxies, like the Triangulum Galaxy M33 and dozens of dwarf galaxies, the Milky Way and Andromeda form the local group of galaxies. These neighbors interact gravitationally in a slow cosmic dance. At the moment, Andromeda and the Milky Way are drawing closer to each other. Andromeda is on a collision course with us, moving at about 110 kilometers per second toward the Milky Way, as indicated by its blue shift. It's one of the few external galaxies that is blue shifted, meaning its light is slightly squeezed to shorter wavelengths because it's coming nearer. This might sound alarming, but fear not. The time scale for any collision is billions of years. What it tells us is that gravity has overcome the expansion of the universe at our local scale. The Milky Way and Andromeda are gravitationally bound and falling together, rather than being carried apart by a cosmic expansion. Gravitational interaction between our galaxy and others can take many forms, even before a direct collision. For example, each galaxy's halo of dark matter and outer stars can exert tugs on the other. If, say, a dwarf galaxy passes by, the Milky Way's gravity can tidally strip stars from it, creating streams. Likewise, the presence of Andromeda and the Milky Way in proximity might be influencing each other's outer halos, slightly even now, though at 2.5 million light-year separation, they're just feeling the first gentle pulls. One clear sign of gravitational interaction is the fate of the Sagittarius dwarf spheroidal galaxy, a small satellite galaxy that is currently being cannibalized by the Milky Way. It's on an orbit that has taken it through the Milky Way's disk multiple times, and each pass rips away some of its stars, adding them to our halo. Eventually, that dwarf will merge entirely, its stars becoming part of the Milky Way's outer regions. The Magellanic Clouds, the large and small Magellanic Clouds visible from the southern hemisphere as smudges in the sky, are two irregular dwarf galaxies orbiting the Milky Way. Their interaction with us is creating the Magellanic Stream, a long ribbon of hydrogen gas drawn out by tidal forces, trailing behind them as they orbit. This stream arcs over the sky and is evidence that the Milky Way's gravity is tugging material off these galaxies. Andromeda itself likely has a similar entourage of dwarfs and has also devoured some in the past. In fact, galactic interactions and mergers are a key theme in how large galaxies evolve. The Milky Way's disk and spiral structure suggest it has had a relatively calm recent history, no major merger in the last approximately 10 billion years, but it is still interacting with small satellites. Each interaction leaves imprints. Rings of stars, streams, or altered motions of stars in the outer disk. Some studies suggest maybe the Milky Way's disk warp, it's slightly bent, could be due to interactions with a passing dwarf galaxy or the tidal pull of the Magellanic Clouds. Our galaxy and Andromeda are the dominant masses in the local group, and they are mutually pulling on each other. Andromeda's gravity affects objects in our galaxy's outskirts, and vice versa. Smaller galaxies in the local group tend to orbit either the Milky Way or Andromeda. For example, the Milky Way has over 50 known satellite galaxies. Most are tiny dwarf spheroidals, like Draco, Ursa Minor, Carina, etc., orbiting it. These satellites feel the Milky Way's pull strongly. Some are in precarious positions, and will eventually merge with us. Andromeda similarly has many satellites. There's even a bit of evidence that the Triangulum Galaxy, M33, a spiral smaller than ours, might be a satellite of Andromeda, or at least is influenced by it. One remarkable fact. Although Andromeda and the Milky Way are moving toward each other, within the local group everything isn't simply falling together. There's also orbital motion around the common center of mass. The local group's center of mass lies somewhere between us and Andromeda. Both galaxies orbit that point in a slow do-si-do. However, their mutual attraction will eventually cause them to meet directly. This leads us to the next topic, the eventual collision. In the distant future, two great spiral galaxies will merge and become one. Andromeda and the Milky Way are destined to collide and combine into a new form. The evidence for this impending collision comes from precise measurements of Andromeda's motion. As noted, Andromeda's light is blue shifted, indicating it's heading toward us at about 110 kilometers per second, around 200 to 50,000 miles per hour. For a long time, astronomers weren't sure if Andromeda was also moving sideways relative to us. A sideways motion could mean the galaxies might just have a close flyby or miss each other. But Hubble Space Telescope measurements of the positions of stars in Andromeda over several years determined that Andromeda's tangential, sideways motion is very small. This implies it is almost on a direct collision course. Calculations suggest that in roughly 4 to 5 billion years, the cores of Andromeda and the Milky Way will pass through each other, and over the following billions of years, they will merge into a single larger galaxy. What will this collision be like? It's a slow, ghostly intermingling rather than a sudden crash. When galaxies collide, stars almost never hit star to star because the distances between stars are so huge. Instead, the two galaxies will pass through one another. Their gravitational forces will distort each other's shapes dramatically. The Milky Way's spiral arms and Andromeda's disk will be pulled and warped into long tidal tails. There will likely be a burst of new star formation as clouds of gas in each galaxy slam into one another and compress, perhaps igniting a brilliant wave of new stars, and even feeding the central black holes, so they light up as active galactic nuclei for a time. Over a few billion years of this dance, dynamical friction, gravitational interactions that transfer momentum, will cause the two galaxy cores to spiral together until they coalesce. Simulations indicate that by around 6 billion years from now, Andromeda and the Milky Way will be merged into a single object, probably an elliptical galaxy, sometimes nicknamed Milkdromeda by enthusiasts. The thin disk and spiral structure will be gone, transformed into a puffier, random orbit system of stars, much like giant elliptical galaxies we see elsewhere. The supermassive black holes of each galaxy, Milky Way's Sag-A and Andromeda's black hole, which is even larger, will eventually spiral around each other and merge, forming an even more massive central black hole in the new galaxy. The evidence supporting this scenario includes not only Andromeda's measured approach speed and negligible transverse speed, but also the fact that galaxy collisions are commonly observed in the universe. We see many galaxy pairs in various stages of interaction, some just starting to touch, others well into merging. The physics is well understood through simulations. Our local group is small enough that Andromeda and the Milky Way are gravitationally bound, and not participating in the universe's expansion relative to each other, so a future merger is expected. In fact, recent studies, using data from Gaia spacecraft and others, suggest even the Triangulum Galaxy, M33, might get involved, possibly being flung into a wider orbit or even merging later with the Milky Way Andromeda remnant. The exact outcome for M33 is uncertain. It might orbit the merged giant or also fall in eventually. One might ask, if this collision is so certain, are there uncertainties? The main uncertainty was the timing and exact angles. With improved measurements, the timeline of approximately 4 billion years for first close approach, and approximately 6 to 7 billion for final merger is generally accepted as v2gggsfc.nas.gov. There is some small uncertainty in the transverse motion. A 2020 study using Gaia data suggested maybe the collision might be more of a glancing blow and take longer to settle, but generally a merger is very likely. A recent 2025 paper even argued there's a chance, roughly 50%, that maybe a direct collision might not happen within 10 billion years if certain motions and influences, like the Large Magellanic Cloud's gravity or the presence of other unseen masses, are considered. However, even if the first pass isn't a bullseye, the mutual gravity will almost certainly bind the galaxies into one system eventually, unless something ejects one of them. For a human or even solar system scale perspective, this collision is far enough in the future that the Earth might not even exist in its current state. the sun will have evolved into a red giant around 5 to 7 billion years from now. But if some far future observers were around, what a sight it would be. As Andromeda comes closer, over millions of years it would grow from a small fuzzy patch in the night sky to a large majestic object. Eventually, perhaps it would span the sky. During the merger, new star formation would create brilliant star clusters and nebulae. The night sky could be ablaze with many new stars, and perhaps different colors from glowing gas clouds. Over long times, constellations would change beyond recognition as stars from Andromeda mingle with ours. In the end, the sky might look more like that seen from an elliptical galaxy, a more uniform distribution of stars rather than a concentrated Milky Way band. After the merger, our sun, if it survives the red giant phase and is still around and not thrown out of the galaxy, would find itself in a very different environment, perhaps in the outer halo of the new elliptical galaxy, or still in some stream. However, the chances of our solar system being directly affected by collisions or near misses of other stars during the merger are quite small. The distances between stars are huge, so even in a collision of galaxies, individual stellar collisions are exceedingly unlikely. Our solar system might sail through largely undisturbed gravitationally, though the overall night sky and positions of neighboring stars would change dramatically. In short, the evidence of Andromeda's blue shift and proper motion measurements by Hubble have convinced astronomers that a Milky Way Andromeda collision is on the horizon, cosmically speaking. It's a slow inevitability, a great example of gravity's long reach. The result will be the transformation of our galaxy into a new form. For now, though, we are at a peaceful stage, each galaxy minding its own business apart from gravitational pulls on their satellites. It's like two giant starships on a slow collision course, currently separated by a substantial distance, but inevitably meeting due to the pull between them. This upcoming event tells us that even galaxies have lives that include unions and metamorphoses. It's a beautiful thought that in the far future, the Milky Way will not exist in its current form, but will be part of an entirely new galaxy, forged from the melding of two spiral beauties. When we peer out into the Milky Way, our view is not crystal clear. It's as if the galactic landscape is partly shrouded in a mist. This mist is formed by interstellar dust and gas, which fill the plane of the galaxy in patchy clouds and complexes. Interstellar dust grains, tiny particles of carbon, silicon, and other elements drift in space and tend to collect in the galactic disk, especially in spiral arms where star formation occurs. These dust grains are extremely effective at blocking and scattering visible light. As a result, when we try to look toward the center of the Milky Way in visible wavelengths, dense dust clouds block our line of sight, creating dark blotches in the starry band. This is why the Milky Way appears divided by dark rifts, particularly the Great Rift visible in the summer Milky Way. Those are dust lanes obscuring the bright star clouds behind them. For a long time, this dust made it impossible to see what lies at the galactic center in optical light. Early observers with telescopes saw dark gaps and assumed maybe there was just less there, but in truth, it was dust hiding a wealth of stars. It wasn't until the 20th century that astronomers like Harlow Shapley used indirect methods, like globular clusters distribution, to infer where the center was, behind the dust in Sagittarius. And in more recent times, using infrared telescopes and radio telescopes, we have been able to penetrate that dust and finally observe the center, discovering Sagittarius A and the orbits of stars around it, for example. So how does dust and gas affect our observations? Essentially, it causes extinction, dimming, and reddening of starlight. Light from distant stars in the disk has to pass through clouds of dust. The dust grains scatter blue light more than red light. Blue light has shorter wavelengths, closer to dust grain sizes, so it's scattered out of our line of sight more easily. Thus, a distant star might appear much dimmer and redder than it truly is, because its blue light has been stripped away and only the redder light came through. This is called interstellar reddening. Astronomers have to account for this when measuring star brightnesses and colors to infer distances or ages. In the most extreme cases, dust completely obscures objects. For example, the center of the galaxy, with its dense star cluster around the black hole, is hidden behind dust clouds in visible light. We only manage to study it by observing in infrared, which penetrates dust better, and in radio waves and X-rays for certain phenomena. The famous image of the Milky Way's center, taken by the Spitzer Space Telescope in infrared, shows a bright, chaotic region that is entirely invisible in ordinary optical photographs. Interstellar gas, mostly hydrogen, also affects observations, but in a different way. Gas itself can be transparent if it's not too dense, especially if it's ionized hydrogen or hot thin gas. Neutral hydrogen gas does absorb some specific wavelengths, like ultraviolet, and can emit radio waves, like the 21 centimeter line. It doesn't block optical light as effectively as dust. The main obscurer is dust. However, gas often coincides with dust. Dust resides in gas clouds. Because of dust and gas, observing the Milky Way's structure from within is challenging. We cannot simply take a picture of the whole galaxy from our vantage point. Our view outward is like trying to see the structure of a forest while being deep inside it. And on top of that, the forest is partly foggy, dusty. As mentioned earlier, astronomers compare it to being lost in a forest and trying to map it. We must use clever techniques, looking at various wavelengths using standard candles and mapping gas via radio. For instance, radio astronomy has been a boon. The Milky Way's spiral arms were first clearly delineated by maps of neutral hydrogen gas, HI, using the 21 centimeter radio line, which is not impeded by dust. By looking at radio, astronomers in the mid-20th century could detect concentrations of hydrogen and their velocities, thereby infer spiral patterns in different directions. Infrared surveys like those with the COBE and Spitzer satellites could see through dust to the distribution of stars, revealing the central bar and overall disk light. Despite dust's nuisance for visible light, it's also what makes the Milky Way photographically interesting. Those dark lanes add contrast and mystery to Milky Way images. But for understanding, we have to peel the veil. Tools like the ESA Gaia mission measure parallaxes of stars, mostly in optical, but Gaia's sensitivity can be limited by dust for distant stars. There are ongoing efforts to create 3D dust maps of the Milky Way by using the colors of stars to deduce how much dust is along various sight lines. These dust maps help correct observations for extinction and give an idea of where dense clouds lie. When it comes to observing other galaxies, our Milky Way's dust can even block external view. If a galaxy lies near the Milky Way's plane, the zone of avoidance, it's hard to see because our own galaxy's dust is in the way. Similarly, from outside, if an alien civilization looked at the Milky Way, they'd see dust obscuring parts of it. Particularly, they'd notice the dust lanes that cut across spiral arms in the central band. Interstellar dust and gas also create beautiful objects and nebulae, which are lovely to observe but are effectively fog banks in space that hide what's behind them. For example, the great rift that splits the Milky Way lengthwise from the constellation Cygnus down through Sagittarius is caused by several large molecular clouds full of dust that absorb light. Behind those clouds are millions of stars we cannot see in visible light. Only by using infrared surveys can we count those hidden stars. In summary, interstellar dust acts like cosmic clouds or fog, hindering our optical view of the Milky Way's true glory. It reddens and dims starlight, making distant stars harder to study. To fully appreciate and map our galaxy, astronomers turn to other wavelengths. Infrared, which can penetrate dust. Radio, to see gas structure in dust-shrouded regions. And X-rays, to see energetic phenomena behind dust. Each provides a piece of the puzzle. Thus, dust and gas impose a serene kind of privacy to parts of the galaxy. One must listen in radio or feel it in infrared to know what lies beyond the veil. It's a bit like a dreamy haze. It makes direct vision blurry, forcing us to use other senses. But thanks to technology, we have lifted the veil in many areas, revealing the bustling center and far side of the Milky Way that were once hidden entirely. When you look up at the Milky Way's dark lens, you can imagine beyond them thousands more stars unseen. Those obscuring dust clouds, while troublesome for astronomers, also serve as the raw material for future stars. Within them, new suns and planets are likely forming, destined to one day light up and perhaps clear away the very dust that birthed them. In that way, the dust and gas are both impediments to vision and the seeds of creation, adding to the gentle cyclic story of our galaxy. Imagine trying to draw a map of an enormous forest while standing among the trees. You can see your surroundings, but not the entire layout of the forest. This is exactly our challenge in mapping the Milky Way. We are inside it, embedded about 26,000 light years from the center in the Orion Arm, and we can't simply step outside and take a photograph of the whole galaxy. Yet over time, astronomers have developed ingenious methods to chart our galaxy's structure and content, turning the seemingly impossible task into a success story of discovery. One approach has been to use what the universe gives us as natural beacons, certain stars or objects with known brightness. These are often called standard candles. For instance, Cepheid variable stars are pulsating stars whose intrinsic brightness can be determined by the period of their pulsation. By comparing how bright a Cepheid appears to us versus how bright it truly is, we can deduce its distance. Dimmer appearance means further away. Cepheids helped establish the distance to globular clusters and nearby spiral arm segments, thus outlining part of the Milky Way's structure. Another class of standard candle is RR Lyrae stars, found often in globular clusters. They have roughly uniform true brightness, so they are handy for gauging distances to those clusters. The 21 centimeter radio line of neutral hydrogen H1 has been a vital tool. Neutral hydrogen throughout the galaxy emits radio waves at this wavelength. By mapping 21 centimeter emission in different directions and using the Doppler shift of that emission, astronomers can infer the velocity of gas relative to us and, with some assumptions about galactic rotation, figure out where that gas is located along the line of sight. This technique, developed in the mid-20th century, allowed the first rough plots of spiral arm segments in the Milky Way. Effectively, the hydrogen gas revealed the spiral pattern, even though we cannot see the spiral arms directly from our vantage due to dust. It was through such painstaking radio observations that we realized our galaxy likely has multiple spiral arms. Initially thought 4 major arms, though now we think 2 major and several minor arms. And even that has a barred center. Another method is parallax, the most direct way to measure distance. Parallax is the apparent shift of a nearby object against distant background objects when viewed from different positions. For stars, we use Earth's orbit. Observe a star now, then 6 months later from the opposite side of Earth's orbit, and note the tiny shift in the star's position relative to more distant stars or quasars. Half of that angular shift, in arc seconds, is the parallax, and corresponds to the star's distance. Distance in parsecs equals 1 over parallax in arc seconds. This method has been employed since the 19th century for the nearest stars, but only in recent times. With space telescopes, it has become incredibly precise. The European Space Agency's Gaia mission, launched 2013, is currently measuring parallaxes for over 1 billion stars with unprecedented accuracy. Gaia's data is revolutionizing our map of the Milky Way. It's providing a 3-dimensional model of the positions and motions of stars in our neighborhood and farther out. Already, Gaia has helped discover fine details like streams of stars, remnants of dwarf galaxies, the warp of the galactic disk, and patterns in how stars move that hint at past interactions. Infrared surveys like the 2 MASS and COBE/DI or RBEMZ have mapped the distribution of stars through dust. Microwave observations, like with the Planck satellite, have mapped dust itself via its thermal emission, which combined with stellar reddening data gives us 3-dimensional dust maps. X-ray and gamma-ray telescopes have charted high-energy processes, highlighting things like the aforementioned Fermi bubbles. It truly has been a multi-wavelength adventure. Each wavelength sees a different aspect of the galaxy. Optical surveys see billions of stars but get blocked by dust in certain directions. Radio surveys see gas structure and penetrate dust. Infrared surveys see cooler stars and dust glow. Ultraviolet surveys pick up hot young stars and tenuous hot gas. X-ray surveys reveal violent endpoints like supernova remnants in the hot halo. By combining all these, we can piece together the puzzle. Historically, we also use the distributions of globular clusters to find the galactic center. Shapley's work around 1918. By noting that globulars are concentrated toward Sagittarius, Shapley determined the center of the Milky Way lies in that direction at a distance of tens of thousands of light years. A discovery that moved us from a Copernican shift, that not only are we not the center of the solar system, but we're not the center of the galaxy either. Mapping spiral arms from within is tricky because we can't see their full extent, but astronomers identify clusters of OB stars, hot, bright stars that live short lives, so they must be near where they formed. Are they near spiral arms, as well as nebulae and molecular clouds that trace arms. By cataloging these and using distances from things like parallax, Cepheids, etc., we outline segments of arms. For example, the Perseus arm is identified by concentrations of young star clusters and nebulae with certain distances and longitudes. The structure is still being refined. Even in the last decade, data from Gaia and other surveys have clarified that our Milky Way might have only two dominant arms, Perseus and Scutum Centaurus, and smaller arm segments, like Sagittarius and our Orion Spur. It's humbling that even now, the exact structure isn't fully settled. It's like we are cartographers mapping a land while walking on it, gradually filling in gaps. One cool modern development: astronomers have even mapped the Milky Way's warp. The disk is not perfectly flat. The outer regions are bent like a subtle S shape, or like a warped record. This was detected by looking at the positions of gas and stars. Gaia helped by seeing that far outer disk stars deviate from the main plane. The warp might be caused by interactions with satellite galaxies or leftover tidal effects from the past. In addition to structure, mapping the motion of stars, kinematics, has told us about mass distribution via rotation curves. By measuring how fast stars and gas orbit at various radii, again through Doppler shifts, we found the rotation curve stays flat at larger radii instead of dropping off. A key evidence for dark matter. So in mapping, it's not just positions, but also velocities that matter. So how do we guide a listener through this mapping in a gentle way? Perhaps by analogy. We started essentially stargazing, noting patterns, then using standard candles like lighthouses to gauge distances, then listening to cosmic radio waves to see the layout hidden by fog. And now, with spacecraft like Gaia, we perform an accurate land survey of the galaxy's stars. It took many years and many clever leaps to get from guessing our place to measuring it precisely. For a dreamy tone, one can think of astronomers as cartographers of the night, mapping unseen coasts by the stars. Bit by bit, like ancient explorers mapping the continent from within, we have charted the spiral arms, located the central bulge, estimated the halo's extent, and found our position in this vast scheme. There's beauty in the methods themselves. Parallax is literally using Earth's orbit as a giant baseline to triangulate stars. A simple geometry concept yielding cosmic distances. And Cepheids are like steady beacons blinking out thy distance codes. So now we have an astonishing mental map. We know the Milky Way is a barred spiral about 100,000 light-years wide. We know where our major arms are and that we are in a minor arm segment. We've mapped the center's bar, about 10,000 light-years long. We've cataloged structures like the local arm, Orion Spur, we're in, the Sagittarius arm inward of us, Perseus arm outward of us, etc. We have even named spurs, splits, and minor extensions as data improves. The mapping continues. Projects like Gaia still are refining distances and discovering new star clusters or streams. In summary, astronomers map the Milky Way using a combination of distance measurements, parallax, standard candles, multi-wavelength observations to see through dust, and the study of object distributions and motions. It's as if we slowly illuminated the forest by using lanterns, standard candles, and sound, or radio, and now have a fair blueprint of our cosmic forest. From the inside looking out, we've identified the forest clearing, the center, and the trails, spiral arms, even though we can't get a bird's eye view. It's a triumph of science that we, tiny creatures on a planet, have deduced the structure of the colossal galaxy we inhabit. The Milky Way is a vast stellar ecosystem containing just about every type of star you can imagine, at every stage of life and death. Floating among them are the ghosts of stars, the remnants left when stars expire. Let's gently drift through this stellar menagerie. First, the stars themselves. The most common stars in our galaxy are the smallest ones, red dwarfs. These are cool, dim stars of spectral type M, often with less than half the sun's mass. They far outnumber all other types. In fact, red dwarfs account for an estimated 60 to 70% of all stars in the Milky Way. Because they shine so faintly, none are visible to the naked eye from Earth, except maybe in exceptional cases, if extremely close. They contribute only a small fraction of the light, but they are the silent majority in terms of population. These stars live extraordinarily long lives, much longer than the current age of the universe. So almost all red dwarfs that ever formed are still around, burning their fuel slowly. And then there are sun-like stars, yellow dwarfs, like our sun, a relatively average star in brightness and temperature, spectral type G. These are fewer in number than red dwarfs. Perhaps 5 to 10% of stars are sun-like, but because they are brighter, they make a noticeable contribution to the galaxy's light. Our sun is one of those billions of middle-aged main sequence stars. Around such stars, planets can form. Indeed, the sun's presence reminds us that countless other solar systems are likely out there in the Milky Way. Moving up in mass, blue and white stars, spectral types O, B, A, are the glamorous but short-lived stars. O-type stars are very massive, 20 plus times the sun's mass, and extremely hot and luminous, shining blue-white. They are rare, a tiny fraction of a percent of stars, because they burn out quickly, in a few million years, or tens of millions at most. B-type stars are also bright and bluish and somewhat longer-lived, but still short on cosmic timescales, maybe approximately 100 million years. These massive stars tend to be found in the spiral arms, especially near star-forming regions, because they don't wander far from where they were born. They die before drifting too far. They often appear in young clusters or associations. When you see the blue glow of a spiral arm in a photograph of a galaxy, you're seeing these hot stars. While scarce in number, they heavily influence their environments with strong ultraviolet radiation and stellar winds, often sculpting the surrounding gas or triggering new star formation. After main sequence, adult life. Stars eventually age into giants. Red giant stars are what happens when a sun-like star exhausts hydrogen in its core and starts fusing helium. The star expands and cools at the surface, becoming a large, luminous orange-red star. Many of the stars in the bulge are red giants, hence the bulge's golden hue. Red giants are common in the sky. For example, Arcturus and Aldebaran are red giants. In the Milky Way, an older stellar population will have many red giants, since that's a phase for stars, maybe 1 to 8 times the mass of the sun as they age. There are also supergiants, extremely luminous and large stars that can be of various colors depending on temperature. Red supergiants, like Betelgeuse, blue supergiants, like Rigel, etc. These are the evolved forms of the most massive stars, and they are destined to explode as supernovae. They are relatively rare and often found in star-forming regions or OB associations. Now the stellar remnants, these are the endpoints, white dwarfs. When a sun-like star, up to about 8 solar masses initial, dies, it expels its outer layers, often creating a beautiful planetary nebula, and the core shrinks into a white dwarf. A white dwarf is basically the hot core left, about the size of Earth, made mostly of carbon and oxygen, for typical ones. It's extremely dense. 1 teaspoon of white dwarf material would weigh tons on Earth. White dwarfs no longer sustain fusion. They simply cool down slowly over billions of years. Our galaxy is filled with white dwarfs, since every low to intermediate mass star eventually becomes one. It's estimated there are many millions, if not billions, of white dwarfs in the Milky Way. They're hard to detect unless fairly nearby, or part of a binary, because they are faint and emit mainly in white-blue, hot ones, and eventually red, cooling ones. One example of a visible white dwarf is Sirius B, the companion to Sirius. White dwarfs can be thought of as the corpses of average stars. Very common, but they only shine by residual heat. Over extremely long times they cool to become black dwarfs. None exist yet because the universe isn't old enough. Neutron stars. When a star more massive than about 8 solar masses goes supernova, its core can collapse into a neutron star, if initial core is 1.4 to 3 solar masses. A neutron star is even denser than a white dwarf, about the size of a city, 10 to 20 kilometers across, with mass approximately 1.4 times the Sun or more. It's essentially a giant atomic nucleus made mostly of neutrons. Neutron stars can manifest as pulsars, rapidly spinning neutron stars emitting beams of radiation, which we can detect via radio pulses, or sometimes X-rays and gamma rays. The Milky Way likely has hundreds of millions of neutron stars scattered throughout, especially in the disk. Remnants of massive stars that went supernova. We only detect a fraction of them, the pulsars whose beams sweep Earth, or ones in X-ray binaries. But their presence is part of the galaxy's life cycle. Each supernova that birthed a neutron star also seeded the interstellar medium with heavy elements. Neutron stars can also collide or merge, especially if in binaries, producing gravitational wave events, like the famous 2017 detected neutron star merger, and leaving exotic objects, black holes, stellar mass. If a star is very massive, core greater than approximately 3 solar masses after supernova, it might collapse further into a black hole. These are stellar black holes, distinct from the supermassive one at the center. The Milky Way is expected to harbor a vast number of stellar black holes as well. Recent studies, including gravitational wave detections of black hole mergers, suggest many stars produce black holes of perhaps 5 to 30 solar masses. It's estimated the Milky Way might have tens of millions, possibly up to 100 million black holes of stellar mass wandering its expanses. Most are solitary and invisible, unless they accrete matter from this companion star, which can make an X-ray binary where the black hole or neutron star draws gas off a normal star, emitting X-rays. So far, only a few dozen stellar black hole candidates have been identified in X-ray binaries or via gravitational lensing. One was recently measured when it passed in front of a background star, causing a lensing effect, confirming an isolated black hole at about 7 solar masses. So they are out there, essentially dark, unless you know how to look. Brown dwarfs. Not exactly remnants, but substellar objects, failed stars that didn't have enough mass to ignite hydrogen fusion, below approximately 0.08 solar masses. They bridge the gap between the largest planets and the smallest red dwarfs. Brown dwarfs emit mostly infrared and are very faint. The Milky Way likely has a huge population of brown dwarfs, perhaps comparable to stars in number. They add to the dark objects in our galaxy. Not dark matter, but dark in the sense of not shining bright. They slowly radiate away their heat of formation. We detect some in infrared surveys, especially near us. So indeed, the Milky Way is peppered with these stellar remnants, white dwarfs by the billions, neutron stars, and black holes by the millions. They are largely unseen but contribute mass. For instance, in the thick disk and halo, old white dwarfs and neutron stars are part of the stellar halo mass. We also have star clusters, not remnants but worth mentioning. There are open clusters, groups of young stars born together found in the disk, and Gene in the Pleiades. They often disperse after a few 100 million years. and globular clusters, discussed earlier, which are ancient star balls in the halo. Open clusters give the spiral arms their sparkle of blue stars, while globular clusters dot the halo as ancient outposts. Another aspect of our galaxy's stellar content. Stellar populations differ by region. The disk has mostly a population of 1 stars, younger, more metal-rich on average, including massive stars, and the Sun. The halo and bulge have more population 2 stars, old, metal poor. But in reality, there's a continuum. The bulge actually has some surprisingly metal-rich stars too, just old but enriched. The halo has extreme metal-poor stars, some of which may be nearly as old as the galaxy, formed shortly after the Big Bang, containing almost no heavier elements, like HE1523-0901, a halo red giant with extremely low metal content, but around 13 billion years old. Cosmic recycling. One can mention how stars return material to the galaxy. Massive stars explode in supernova, distributing heavy elements, carbon, oxygen, iron, etc., into space, which later condense into new stars and planets. Lower mass stars blow off outer layers and planetary nebulae, gently enriching space with elements like carbon and nitrogen. Thus, each generation of stars adds metals to the galaxy's gas, meaning newer stars like the Sun have more heavy elements, and the Sun is metal-rich compared to older stars, which is why it had solid material to form planets. The Milky Way has gone through many such generations, especially in the disk. The halo stars, being the earliest, have far fewer heavy elements. They formed before supernovae had a chance to enrich the gas much. From a peaceful narrative view, we could imagine drifting among various stars, flying past a cool red dwarf glowing dimly red, then approaching a brilliant blue giant star whose light is strong and fierce, then maybe witnessing the eerie presence of a pulsar blinking its lighthouse beam, or coming across a white dwarf with a faint bluish-white glow. We might envision how after eons, a star like our Sun swells into a red giant, then sheds a shimmering shell, a nebula, and leaves a tiny white dwarf at center, a cosmic ember cooling through time. And around us, in the darkness, might lurk an invisible black hole, detectable only by its effect on nearby matter or gravitational lensing of background starlight. All these forms, from star wombs, nebulae, to vibrant young stars, to dying stars and leftover remnants, populate the Milky Way, making it a dynamic, ever-changing system. The stars we see in the night sky are a partial sample bias toward the luminous ones. The real Milky Way has countless faint and exotic objects unseen to human eyes, but present nonetheless. Our own Sun is accompanied by an entourage of planets and countless asteroids or comets, and by extension, many stars in the Milky Way likely have planets. Indeed, exoplanet surveys tell us that planets are very common, so one could say the Milky Way also contains planets beyond counting, from hot Jupiters to icy mini-Neptunes to rocky Earth-like worlds. It's quite poetic that out of the stardust, planets and possibly life, like on Earth, emerged. We humans are literally made of heavy elements forged in stars long ago, so we are a product of this stellar population as well. Given the tone, we may not want to get too technical, but emphasizes variety in life cycle. Stars are born from clouds, life shining their light, then fade and sometimes explode, leaving behind gentle remnants. White dwarfs cooling like spent coals, or neutron stars ticking like cosmic clocks, or black holes where even light is trapped. These remnants quietly drift in the galaxy's dark, a testament to past brilliance. That sort of imagery. We can also mention specific known example in calm passing, like when you gaze at the sky, the red star Betelgeuse shows what a supergiant looks like, and faint bluish Sirius B, with a telescope, reveals a white dwarf, but maybe too factual for bedtime. Better focus on general concept. The Milky Way is full of stellar life at all stages. It's like a forest with trees and saplings and rotting logs, remnants, a cycle of star birth and death that enriches the galaxy. One interesting final piece. The Milky Way's stellar halo includes some hypervelocity stars. a rare few that have been flung out of the center, perhaps by black hole interactions, and travel fast enough to eventually leave the galaxy. These are like the wild renegades of the stellar population. But enough details. The key takeaway: the Milky Way contains a vast diversity of stars, far more dim ones than bright ones, and many leftover remnants of former stars. This mix of objects is what makes the galaxy shine and what has seeded our planets and possibly life. So as a listener drifts to sleep, they can imagine the gentle glow of billions of distant suns, and in the quiet spaces that in between, the unseen presences of stellar embers and black holes. It's a cosmic circle of life. Stars born from the ashes of previous generations, shining, then returning material to space in a continuous, slow, cosmic rhythm. Finally, let's place our Milky Way in the context of the expanding universe. We know from cosmological observations that on large scales galaxies are flying apart. As space itself stretches, the farther a galaxy is, the faster it recedes. Hubble's law. However, when we zoom into our local group, we find a different situation. Our Milky Way and Andromeda, and satellite galaxies, are bound together by gravity and not participating in the general expansion. Cosmic expansion largely affects regions of space that are not gravitationally bound. Our local group, roughly a few megaparsecs in diameter, it's like a little enclave where gravity has halted expansion. Galaxies within the group move under gravity, like our approach with Andromeda, rather than being carried away from each other by expansion. In fact, the local group, which includes the Milky Way and Andromeda as the big players, is in turn part of a larger assembly of galaxies known as the local sheet, or a local supercluster, Virgo supercluster, or more recently Laniakea supercluster, after 2014 definition. The local group itself is moving toward the Virgo cluster of galaxies, or part of our supercluster, at a certain velocity. It's known that the Milky Way, along with the local group, is moving at about 600 kilometers per second relative to the cosmic microwave background, CMB. We can tell this because the CMB appears slightly warmer in the direction of our motion, and cooler opposite, the CMB dipole anisotropy. This motion, sometimes called the peculiar velocity of the local group, indicates that our galaxy is gravitationally attracted to some region, like the Virgo cluster or beyond, possibly the Great Attractor region. In fact, the Milky Way and the rest of the local group are fallen toward a concentration of mass in the direction of the constellation Centaurus, the Great Attractor, which is part of the Laniakea supercluster center, at hundreds of kilometers per second. So we have multiple layers of motion. The Earth orbits the Sun approximately 30 kilometers per second. The Sun orbits the galaxy approximately 230 kilometers per second. The Milky Way, with the Sun, orbits the local group's center of mass, maybe a smaller tens of kilometers per second relative to that, if we consider Andromeda and us orbiting each other. The local group moves toward Virgo cluster approximately 100 kilometers per second or so. The local group moves relative to the CMB approximately 600 kilometers per second. All these motions are superimposed, but only beyond the local group, a radius of approximately 2 million light-years, does cosmic expansion become evident. Galaxies outside our local group, and other bound groups, generally recede from us. For example, the Andromeda galaxy is close enough to be bound, coming towards us, but galaxies just a bit further, like those in the next small group or cluster, galaxies in Virgo cluster, subside 50 to 60 million light-years away, are mostly receding. However, because gravity clumps matter, not all galaxies in Virgo are receding from us uniformly. Some, like M86, actually have a component of motion toward us because within Virgo cluster, it orbits around and currently is coming our way relative to cluster center. But the cluster itself as a whole is receding. So what does the Milky Way's motion tell us about cosmic expansion? It illustrates that cosmic expansion is a general trend but is overcome by local gravity on smaller scales. The universe's expansion does not rip apart gravitationally bound systems like galaxies or local groups. Thus, our galaxy is not expanding internally. The solar system isn't expanding away from the sun due to expansion either. All atoms, planets, and star systems remain bound. Even the local group stays bound as a whole, but on scales larger than about 100 million light years. The expansion dominates in clusters of galaxies separate from each other, with space stretching between them. The Milky Way's eventual merger with Andromeda underscores this. While the universe at large expands, our two galaxies will still collide because our local gravity is sufficient to overcome the stretching of space at that scale. On the other hand, if we consider our local group relative to the Virgo cluster, approximately 50 million light-years away. The expansion, plus perhaps gravitational forces, means we will likely not merge with Virgo cluster, but rather maybe slowly drift relative. Some studies indicate the local group might eventually get captured by Virgo's gravity billions of years hence, but cosmic acceleration due to dark energies likely prevents superclusters from growing much more. Yes, dark energy means that expansion is accelerating, so ultimately, beyond a certain distance, galaxies will recede faster and faster. In the very far future, 100 and plus billion years, the only galaxies visible from ours, or what's left of it after merging, might be those bound to us initially, like the other local group members, as everything else speeds out of view beyond the observable horizon. But that's an extremely far future speculation. In simpler terms, one can say, the Milky Way's motion through space shows that while the universe expands overall, our galaxy is part of a gravitationally bound neighborhood that is not flying apart. Distant galaxies outside this neighborhood do recede due to the expansion, but our Milky Way and its nearby companions cling together, not carried with the general flow. If we anthropomorphize, it's like the Milky Way and Andromeda are two dancers slowly moving toward each other in a room, local group. That itself is part of a building, local supercluster, expanding outward. The dancers feel each other's gravity more strongly than the floor's expansion beneath them, so they come together despite the building's growth. From our standpoint within the galaxy, cosmic expansion doesn't affect distances between stars or the orbits of planets. It's an extremely weak effect at such scales, completely overwhelmed by local forces. Only on intergalactic scales does it show up. So when we look at the motion in the Milky Way relative to very distant reference frames, like the CMB, we see a combination of gravitational influences, like being pulled toward denser regions, and the underlying expansion metric. We might mention that our galaxy is part of the Laniakea supercluster, a gravitationally related collection of galaxy clusters, including Virgo, as defined by a certain study. According to that concept, eventually all of Laniakea, including us, is one bound structure in the even grander scheme, and anything outside that is receding away due to dark energy. But to keep it simple, mention a local supercluster, or just say local patch of the universe. Cosmic expansion evidence itself came from noticing that almost all galaxies outside our local group are redshifted, moving away. But Andromeda is a notable exception, blue-shifted, which directly shows that gravitational attraction can locally override expansion. If someone asks, if universe expands, why is Andromeda coming at us? The answer is because on that scale, gravity wins. The expansion is not a force that pushes things apart. It's just space stretching if nothing holds them together. In our case, we are held together with Andromeda, so we don't partake in that separation. A gentle metaphor. Cosmic expansion is like raisins and rising dough, where distant raisins move apart as dough expands. But raisins that are close and stuck together, like clusters of raisins glued, will stay together while the dough expands around them. The local group is a clump of raisins held by gravity. So to lull our listener, perhaps describe how beyond our galactic home, distant galaxies are drifting away. If we could watch over billions of years, the spaces between clusters widen. Yet our Milky Way's immediate family, the Andromeda galaxy, etc., remain bound in a cosmic neighborhood not easily pulled apart. This tells us that the universe's expansion is gentle on small scales, and only shows its hand over to enormous distances, And it hints at the presence of the mysterious dark energy driving expansion. Although that term might be too jarring for a bedtime story, maybe just refer to it as an expansion pressure of the cosmos. We might conclude with the notion that our Milky Way, while moving through space, will stay in company with its local galaxies even as the wider universe expands. Over extremely long times, if expansion accelerates indefinitely, our local group might become isolated, with distant galaxies receding beyond visibility. But that's a melancholy far future scenario, perhaps a better to end on a positive. The Milky Way and Andromeda will merge into a new galaxy, and their combined stars, including perhaps whatever remains of humanity's home star, will continue journeying through an ever-expanding cosmos, carrying on the story of stars even as the universe grows older. To wrap up the script, we can note how the cosmic expansion means that the Milky Way is part of something even larger, the cosmic web. And though bound locally, it participates in the grand motion of the cosmos on the largest scales, the ultimate soothing perspective. Lying under the stars, one can feel at peace that while galaxies far away speed off into the unknown, here at home we are gently orbiting our galaxy's center, secure in our local corner of the universe. The cosmic expansion does not tear us apart. It simply adds to the grandeur that on the vastest scale, everything is drifting like glitter in stretching taffy. Yet locally, gravity ties some glitter pieces together. In a poetic sense, the Milky Way's motion through the universe reminds us how balance is struck between expansion and gravity, and how our home finds itself in a Goldilocks zone of scales, not too big to be taken by expansion, not too small to be insignificant in cosmic flow. So we sail, a galaxy among billions, expanding away from most others, but sailing with a close fleet of companions through the endless dark ocean of space.